Welcome, class, to first week of IMT-212, Metallurgy, the study of steel, even though we're studying also ferrous and non-ferrous, which means iron-based and non-iron-based, like aluminum materials. This is the book by Daniel A. Brandt, the 6th edition. You can get this in the bookstore. You'll need this for the class. And we will start off on Chapter 1. Okay, Chapter 1, History of Metallurgy. So a little bit of background on the first uses of materials in over the course of history. Yeah, lots of times the age in which you live is defined or called by the main material that was being used. So we had obviously, here the term, send you back to the Stone Age. And the Stone Age, if you look at the chart, ended around 2,000 years before Christ, and that's when, obviously, 1,000 years before then. It just shows how there's overlapping time periods here where they're using both. But we can see the Bronze Age overlapped the Stone Age and the Iron Age. So we it looks like the Iron Age ended in year 1000, but I don't know why that would be, because we are still heavily dependent on iron for steel. So this little graph, I don't know, could use a little work. But anyways, that gives you the idea. Maybe because the iron, I would assume maybe they're ending iron at 1000 because that's when steel started to take over. So even though steel is made 90+% out of iron. Alright. Yeah, stones were the original materials for tools, found in nature, in their raw form. They are hard and brittle. They needed better materials for better tools. They used to go and search for stones that they could use another stone in order to knock off a piece that was sharp, and that was a skill. They used to flake it. If you go online, you can find videos of making Stone Age tools. And they had to constantly be searching for these because the tools they would make would break down quickly because they were so hard and brittle. So they needed tools that were better. These tools are very sharp, these out of stone, but they just would not hold an edge for very long. They would, or I shouldn't say that, they would hold an edge, but if you're cutting something like an animal to, skin it, and you hit some bone with that rock cutting instrument, it could chip very easily. Just would not take any kind of abuse. So they were constantly on the move for new stones to make into cutting tools. Okay, yeah, metallurgy is the science and practice of working with metals. Basically, you can't really work with them until you can have them. So extracting metal from its ore was the first step. And there's a link to a video showing of this primitive skills channel that shows a person trying to make some iron the old way, and you can see it's very, very labor intensive, and hence the amazing ability for us now to make tons and tons of steel at relatively low cost. Okay. Alloying and processing the metal to achieve desired properties. We're going to be talking a lot about alloys, which is basically a mixture of metals. Yeah, copper and gold, first metals to be used. Yeah, they're found in nature. You can see this is a piece of copper ore on the right here. Found in nature in metallic form, so they could use them as is. And then they could hammer and forge them into usual shapes and tools because they were malleable. They were able to be formed. Rock and stone you cannot form. It's all you can do is break them into different pieces, but you cannot fundamentally take it and change its shape. Okay, copper and tin ore melted together to produce a bronze. So copper and tin make bronze. It's an alloy. Smelting is the process of extracting metal from its ore. Okay, that was on the last page. Alloying is a process of combining metals or non-metal together to make a different material. Yeah, alloy bronze is stronger than copper. Copper is very soft, pure copper. even the copper wire we have, I believe, is alloyed to some degree. Can't have pure copper. Molten metal is cast into sand molds for cast bronze. So this is how they made, like you can see this little figurine here on the right. Yeah, open face sand molds were the first method of casting. Produce intricate shapes. Yeah, if you could carve a mold, you could make whatever shape you wanted. Large blocks were called ingots for reworking. Yeah, that's a term we still use today, even though we don't do the ingot method very much anymore. Bronze ingots widely traded to regions with no tin. Other alloying elements added to strengthen the copper. Yeah, nickel, one of them. Alright, the Iron Age. First iron products were made from meteoric iron. So basically, if you're lucky enough to find a meteor, you had some quality material there. Yeah, very rare and highly prized for obvious reasons. Not too easy to find meteorites. Even though we get hit all the time, but most of them just burn up in the atmosphere and don't make it to the ground. Okay, smelting iron ore came about 1200 BCE. Iron ore, charcoal, and limestone heated to produce the iron metal. Basically smelting is to remove the iron from the ore being other materials, making up rock. When that becomes removed, it's called slag. More complex than smelting copper, multiple setups, higher temperatures, longer times, a lot more difficult. Difficult to completely remove slag. Yeah, so your melting temperatures for iron is way higher than your non-ferrous metals like aluminum and such. It's like when, as a machinist, you know this very well, that aluminum will melt if you don't keep coolant on it and you run too fast without coolant. It definitely unless you push it really fast to make a thick chip. If you go slow, you tend to melt it instead of cut it. Okay, wrought iron. Yeah, smelted iron forged repeatedly to drive out slag. You guys are used to seeing the blacksmiths with the hammer and anvil, hitting the iron and seeing the sparks fly. That's what's happening when he's hitting that material with the hammer. He's driving out the slag. That those sparks is the slag. So when you hit a piece of material that doesn't have a lot of slag in it, you don't see many sparks. So a high quality iron, a pure iron, won't have those sparks coming out of it, or as many. Produce stringers of iron metal called blooms. Okay, blooms are forged into usable tools, by heating and then working with a hammer generally, or in the modern era with some kind of a press, a hammer press. Wrought iron had a low carbon content. Yeah, it's basically almost nothing. So it's pure iron. It's really pure iron. Wrought iron is really basically pure iron. Yeah, bloom rings were the earliest furnaces for smelting iron ore. Okay. Wrought iron and true steel. Alright, produced root steel by melting in small crucibles. This higher quality iron was slag free. Yeah, the slag is like an impurity that causes weakness. Because think about it, the rock is brittle, and if you've got areas in your steel that's brittle, or your iron is not going to be very strong. Yeah, slag floated to the surface and separated from the metal. So, and this kind of wood steel has a higher carbon content. It's not pure iron. It's got to have some carbon in it to be called a steel. Yeah, much stronger. It was really the first true steel. They really didn't know why they were getting the results they were getting, but they just knew it worked. And you can see the Damascus sword pattern on the sword to the right. That's an obvious tip-off that it's a Damascus steel. Alright, cast iron. Third form of iron. Made using blasts of air to increase furnace temperatures. Independently discovered in Europe, Asia, and Africa. Yes, not sure where it originally started up, but looks like one of those things that was discovered simultaneously because the need was there. Yeah, cast into simple shapes called pig iron. There's a thing in the book about the molds look like little pigs, and that's like suckling on their mother, and that's where the term pig iron came from. Yeah, this iron is not like wrought iron. Wrought iron is like no carbon in it, and steel is some carbon in it. Cast iron is 2 to 6% carbon. So it is a middle of the road. So normally most carbon is going to be around 2%. Carbon, silicon, and other elements. Lowers the melting point, making it easier to cast. Harder and more wear resistant than wrought iron, but very brittle. Yeah, but can take compressive loads, which we will cover later. Okay, iron and steel alloying elements. Carbon is the most important alloying element in iron. Yes, that is the number one um, to make steel is carbon. Typically, like as a machinist, we like to call things like low carbon, medium carbon, high carbon. So normally, like if I'm making fixtures, you don't need anything fancy. Low carbon, like 1018, which we will cover those kind of numbers, what they mean, is fine. You don't need to have something really expensive to make decent fixtures with. So usually to keep the cost down, you go with some kind of low carbon material. And plus it's easier to machine. So typically low carbon is what you're going to see. Most of the steels you see are some kind of low carbon steel. Low levels make wrought iron that is easy to forge. At higher levels increase strength and hardness, and at very high levels cast irons make metal brittle. Yeah, so typically you don't have more than like 1% in steel of carbon. It doesn't take much to totally change the game. All right, the Industrial Revolution in metallurgy. Yeah, basically this permitted the industrialization. If we didn't have steel, I mean, it really was the materials typically lead the way. Usually, machine tools and such are catching up to cutting technology. So, in this case, machine tools are trying to catch up to computer technology, but I digress. Yeah, metals were improved by industrial inventions. Yeah, I mean they kind of worked hand in hand. Steam engines made the steel were safer and more powerful. Yeah, there's a thing in the book about one of these steam engines that exploded because of the steel was just not up to par, and then James Watt made his steam engine out of some crucible steel for the plates riveted together. I'm assuming for the pressure vessel, and that was successful. Okay, puddle iron process developed in the late 1700s, produced larger volumes of higher grade wrought iron. Okay, wrought iron, basically no carbon. Needed better process control. And the Eiffel Tower, ironically, was built in this time and made from puddle iron. A little tidbit. Samuel Morse launched telegraph commercially in 1844. So what did this create the need for? Tons of copper wire. So the copper wire conducted electricity very well and formed long wires to communicate long distances. So here you have an invention that needs a ton of an element that actually, it's funny, the next page, well, actually, did they cover that? Oh, they don't talk about that. Actually, the need for the copper wire, actually, since it conducts electricity well, it actually helped Thomas Edison when he came along with electrical power generation. That then you had electricity which flows well over copper, and the copper helps make the electricity with electric generators. So they kind of worked hand in hand. Yeah, form long wires that communicate long distance. So yeah, obviously the telegraph wires, transformed obviously into phone lines, and now we have the internet lines, obviously. So, but obviously they make the lines smaller and smaller and smaller. Telegraph keys and precision instruments made from brass. Yeah, brass alloy of copper and zinc. So bronze is copper and tin, brass is copper and zinc. Yeah, brass is a very popular machined material. Yeah, easy to cast, easy to form, easy to machine. Definitely easy to machine. It cuts at short chips, so it's very forgiving machining wise. When a material short chips, meaning the chips come out and break off real easy, less chances of them clogging tools and breaking tools. So yeah, it's stronger than copper alone. Not much isn't. I mean, copper is pretty soft. Okay, Bessemer converter. Patent in 1856 by Henry Bessemer. This sort of changed the game as far as making steel. Yeah, changed liquid pig iron into steel, blows air through high carbon iron. That's the key to these, and that's in the old forge or the old uh, um, uh, you had those big bellows to blow the air to keep the heat up. That's part of the deal here. The oxygen reacts with the carbon, producing carbon monoxide and heat, and many other impurities are also removed. So, and then this sped things up. It was very rapid. So then, therefore, the cost of steel greatly decreased, and application of steel greatly increased. If something becomes cheap and it becomes plentiful, then people are more apt to use it versus stuff that is expensive. Open hearth furnace, first operated in 1865 in France. Better quality steel than Bessemer, but much slower. So here, if you want the quality, you're going to have to pay more because it takes longer. But if you need that better quality in order to do what you need to do, it's going to be economically viable. So here it says 8 hours to produce one heat or batch of steel. They still call batches heats. Well, they'll if you have someone say, like, they'll write down the heat number on a piece of material so they know when it was made. Bessemer converter produced a heat in less than an hour, so you're talking 8 times longer versus to do the open hearth furnace. All right, steel in America. Andrew Carnegie. Okay, kind of like the Elon Musk or one of these other tech giants of the day. These guys were the big boys that um, uh, really fueled the economic engine of the country. With the steel and building the steel. He said Andrew Carnegie was just obsessed with efficiency. He kept trying to make the whole thing as efficient as possible. Built the world's largest steelworks in 1875. Homestead Works near Pittsburgh, of course, steel country. Used the Bessemer process, make high volumes of inexpensive steel, and obviously at the same time the railroads were being built, so or added to, because we already had I think we had the Intercontinental Railroad at that time, so lots of need for lots of volume of steel for these railroad rails. Let's see, added open hearth furnaces by ATDF for making higher grade steel, naval armor plates as an example. So obviously need some strength there for a naval vessel. Okay, probably battleship, I would think. All right, electricity and metal refining. Thomas Edison developed the electric generator and distribution system in 1882. So you can see how these different industries were kind of coalescing at the same time. So this became, since you had ability to create electricity, now that became valuable for refining copper. Well, they went hand in hand. The electric current required to refine copper to high purity for electrical applications. So you needed copper for the electrical generation, but then people wanted the copper for communications. So they went hand in hand. Became essential for electrolyting and refining of aluminum. So aluminum is one of those metals that actually, at the time of the founding of the country, when they built no, I shouldn't say that was at the founding, but they built the Washington Memorial. The capstone is made out of aluminum, and that aluminum was worth more than gold at the time because they didn't have electrical power like we did at this time. So the cost of aluminum dropped by 90%. Applications for aluminum increased. Like I said, anytime something's cheap, it gets more widely used. So this was a big game changer in the last century. In 1950s, 1952, Austria installed the first basic oxygen furnace, adopted in Europe, rebuilding steelmaking after World War II. So, if you think about it, Europe was bombed into oblivion, so they started from scratch. So they started building these basic oxygen furnaces after World War II. It's basically the same as that Bessemer converter, but using pure oxygen instead of air. Much faster, more efficient than the open hearth. And of course, U.S. steelmakers didn't adopt it till '64, probably because they already had plenty of these other furnaces around, and didn't want to change over, but they had to probably to compete. Continuous casting. this is where you're continually casting steel, or iron and steel. You're not stopping. It's just a one continuous process. Uh, yeah, started this in 1967. Hard to believe. I mean, I was born in '66, so hard to believe that that was when they started doing this. In the following 40 years, mostly produced your traditional large ingot casting. Uh, yeah, that used to be they produce a big, just one big giant piece at a time. And actually, my grandmother worked at Alcoa in the 40s during World War II, and she would drive some big forklift that would move these giant aluminum ingots around. So, kind of a little interesting thing. Electric arc furnace. Okay, first commercial electric arc furnace charged with scrap steel went into production. Okay, oh, charged meaning loaded with scrap steel to make new steel. Led to smaller scale steel mills called mini mills. Used electric arc furnaces fired with steel scrap. So a lot of the steel we have is recycled. Built through the United States, and today mini mills produce nearly 70% of our steel in the United States. So, uh, and I'm sure, yeah, it's amazing that this stuff didn't come around until 1969. So a lot of changes even in our lifetimes. Yeah, here aluminum cans. Yeah, Alcoa built aluminum beverage can production line. Yeah, my great grandmother, she worked at the one in McCook. I'm not sure if it's still there or not. I think it is. Aluminum sheet easier to form than steel. Aluminum cans are lighter, reducing shipping costs. And aluminum cans came to dominate the beverage market. Yeah, and I think it's something like over 90%. It's like maybe over 95% of aluminum cans are recycled. Yeah, and that's good because that takes energy. So if you're concerned about the carbon footprint stuff, you definitely want to be recycling your aluminum because that uses energy in order to create from iron or from ore. Okay, recent developments in additive manufacturing is now come online. Notice 3D printing, but they're doing it with steel now. Makes functional metal parts from powdered metals. Computer-directed laser or electron beam strikes selected areas on a flat surface covered with a fine powder. So they basically deposit the powder. Yeah, here, metal powder reservoir rises slightly, pushing a thin layer of metal powder above the lip of the reservoir. Step 2, a rake roller pushes the metal powder from the top of the powder reservoir deposits in a thin layer along the top of the build platform. So here you can see this little green thing. It's like a rake taking a small amount of material and depositing it here, and then the laser, with a program for motion, melts or fuses the layer of metal powder to the layer beneath as it's needed to create the part. So it builds it layer by layer by layer, and this build platform lowers every time it builds a layer. This platform goes down. That's basically how your 3D printing works, except I think the ones with plastic just move themselves up. They don't have the rake moving the powder and such. They're fed with a wire or cable like of raw plastic. So, but this is the same concept basically. And that's it. So your assignment for this week is to read Chapter 1 and do the Chapter 1 quiz. That's it. Thank you very much.